about those QRPA type calculations and also the restricted shell model calculation, which are essentially within a valence shell. And from our experience with low energy electromagnetic response, we know very well that there are induced interactions, or better to say, induced couplings to higher lying states, which shift and fragment the strength quite a bit around. Is that taken into account to some extent?
So only in this case is taken into account, because here they have, although not the best way of deriving an effective operator, but it is the typical way, which worked pretty well in fact. So there are many people submitting today papers describing effective interaction obtained from ab initio, entry and low potentials, using all kinds of techniques more sophisticated than Co-Brown. But if you look, besides some anecdotal better comparison of the experiment, if you look to the overall, if you do an RMS, they are pretty much like Co-Brown.
Yes, okay? But remember that you are not renormalizing the vertices.
Yes,
the self energy you are not having, and consequently you are not renormalizing the vertices. You are using the induced interaction, fine with Hu on Brown, but you are not renormalizing the single particle, and consequently not the vertices.
This is what is done here.
No, that is not renormalizing the single particle, that is renormalizing the interaction.
So this is the equivalent of core polarization for the operator. So what is not done here, which is true, the operator, the bare operator still doesn't have short-range correlation. That's true. But other than that, the typical way of doing things, you usually renormalize your interaction or operator to go from, let's say, 60 major shell to roughly 15.
No, I mean,
after that,
but your single particles have a spectroscopic factor 1 all the time.
Why do you say that? I mean,
well, because you are not attaching anything to them. You are making them interact, but not.
I mean,
but
this is done by the technology of the shell model. They give you the spectroscopic factor turn out to be pretty well.
Yeah, but there are other effects. So you might have direct polarization contributions, self-energies, dynamical self-energies to the single particle state.
You probably have self-energies.
Yeah, but
well,
it's not so evident from that.
I'm a little confused about whether we talk about the effective interaction or the effective operator, because there is no self-energy in the effective operator.
Yeah, but
the effective interaction, yeah, they are. But they are in
your calculation.
Right.
But you should also dress the lines. That's what I'm saying,
yes.
or what Ricardo is saying.
Yeah.
Right.
Mm-hmm.
Just take one line. If you have a single line, you have no effect. And that single line should have a lot of things attached to it. That's the point.
Okay, so this is debatable.
There is one point. This is only second order. I mean, the other renormalization that take into account of self-energy, they go beyond this order. That's it. I mean, if you go beyond this order, you have also this single particle renormalization. If you picture only at second order, that's how the diagrams. That's it. That's the theory.
I'm sorry, I have to stop. Okay, thank you again.